All right, so last time I left off, I couldn't figure out, sometimes when you do double check, you repeat the same error. I've done this on other occasions where I just key in and I keep keying in the wrong thing, and sometimes it's hard to see. I've done this like when I was calculating times for a major timed event, and I screwed up all the times. And this is for a pretty big national gathering where all the times were being recorded and then they were being published. And I kept making the same mistake in calculating people's times because they recorded it in tenths of minutes, and then I had to convert it from tenths of minutes to seconds, something simple. And so I'm always aware of doing that, but sometimes you get into this thing where you just don't see it, and that's why, double checking your answer and then checking to make sure that things match is good. But I went back and just repeated that calculation, did it earlier. And so I want to talk about this one. That was the 250 milligrams of silver chloride solid. And then how many drops of 6.0 molar ammonia it takes. And so this is a KSPF calculation. And the easiest, there are lots of ways of solving this. And so you can get into like very long, but the most direct way is to do it like this, where you just take the KSP, combine it. You could try to do it separate, but if you did it separate, doing it separate is better because then we wouldn't be ignoring the silver ion concentration, the free silver, and that would be better. Because here, when we do it combined, we're going to completely ignore the silver ion concentration. Well, that's okay as long as KSP is very small. Well, this KSP is 1.8 times 10 to the minus 10. That's pretty small, so there's very little free silver generated. And as long as KF is fairly large, and in this case, KF was fairly large, and I forgot to write it down. 1.6 times 10 to the 7. So this gives us silver chloride solid plus 2 ammonia. The diamine, silver plus chloride. And we get the KSPF. This I did write down. The KSPF we had is 0.00288. I'm only allowed 2 sig figs, but I'm going to carry extra. All right, then we set the ice table here. And so we're starting off with 6.0 molar ammonia, and then we have our silver chloride that we need to all dissolve. This starts off with 0 molar and 0 molar. And so at equilibrium, it's 6.0 minus 2s molar, and this is s molar, this is s molar. So the same stuff. So this is going to be the concentration of the diamine silver times the concentration of chloride, which is going to give us s squared over 6.0 minus 2s quantity squared here. And we take the square root of both sides and then solve for s. So taking the square root of both sides and solving for s, I calculate an s value of 0.29078. And then we plug that in here, 0.29078 molar and 0.29078 molar. And then this one comes out to 5.4184. 5.4184 molar. Okay, now when I check the K comes out to 0.00028799. So that K checks out. But this is, you know, this is dissolving a lot more, 0.29 moles. How many moles do we have of the silver chloride? And so we have a lot less. So we don't need a full liter, you know, to dissolve it. And so when we calculate it, we had 250 milligrams of silver chloride, which will convert to grams, so 1,000 milligrams per gram, and then convert that to moles. It was 143.32 grams per mole. And then convert that to liters using the solubility. This solubility is how many moles of diamine silver. Actually, the solubility technically is how many moles of silver chloride we dissolve, which is equal to the number of moles of silver complex in chloride. And so what we can say is that we're going to get 0.29078 moles of silver chloride dissolved per liter. And then convert that to milliliters, 1,000 milliliters per liter, and then convert that to drops, 20 drops per milliliter. And this came out to 119.99. 98, 119. And so everybody got that. And so the way to visualize this is that we can double check these, which we'll do here, but the way to visualize this is like this, probably. So we have this many moles, you know, of silver chloride we need to dissolve. And so that's going to be this solid silver chloride here, AgCl solid. And it's 250 milligrams, which equals 0.0017443 moles. Of silver chloride. All right, then we're going to dissolve that in the 6 molar ammonia. And so what we're going to do is we're going to put in 120 drops. 120 drops is equivalent to about 6 milliliters. It's going to be 5.9989 milliliters. I'm just carrying extra digits because I just want to check this to work out. The 6 molar ammonia. Okay, so what's going to happen there is we expect the silver chloride to all dissolve in this 6 milliliters and form the diamine complex. So we're going to get that to dissolve in this. So we can calculate the molarity of this here. Okay, so the silver chloride is going to convert into diamine silver ion. And the molarity of that is, okay, so we have 0.001743 moles of that dissolved in 5.9989 milliliters, and we'll convert it to liters, 1,000 milliliters per liter. And that's going to give us 0.29077 molar chloride, so 0.29077 molar. So there's a little bit of round off there. It should have been 29078. Check those digits again. But anyway, it's pretty much there. Okay, this is also going to equal the chloride ion concentration. It should be 0.29077 molar chloride. And the ammonia is going to go down because originally it was 6 molar. And so if we calculate how many moles of ammonia we have, and then divide it by how many liters, we end up with we can do that because here we're going to have both complex ammonia and free ammonia. And so the combined total of complex and free ammonia is going to be 6. And so it's going to come out to 5.414 more ammonia, free ammonia left. Yeah. Okay, so one thing that makes this easy is we make the assumption that adding the solid silver chloride does not change the volume. If it did change the volume, that is, if it changed it from 6 milliliters to something else significantly, this isn't going to work, And so this is why a lot of problems will say we're adding solid, and then we're assuming that it's not going to change the volume. All right, so we can reverse this by just checking here. Like, so for example, I can figure out how many drops, or I don't know if it's necessary to reverse. But what we could do is we could just add this to this and then calculate the concentration and we'll see it checks out. So this is the easiest way of doing it. I've done it other ways where you add Z drops, like I was trying, but that's the two equations, two unknowns, is more susceptible to making errors. And so I would recommend doing it like this. This doesn't always work though. For example, here, if the silver ion concentration were significant, it wouldn't work. The book, sometimes the book will do this separately. If we do it separately, that's fine. We don't have to do it combined. But if we do it separately, we have to do it simultaneous. The problem is when you look at the answer in the book, you have 2 different concentrations. So for example, one concentration, like the chloride, is different than the other concentration, like the silver and the second. The chloride, well, actually, these can be different, but the combined concentration is silver. And so sometimes when you do it separately, you can't do them independently. They have to be done, simultaneous. And so if you take a look, I don't know who did the solutions. It obviously wasn't Petrucci, I'm sure, but they, with a solutions manual like that, they hire a lot of people to work out the answers, and sometimes the people might get it wrong, and so that's why I said earlier that there's some problems in the book. I think with this particular problem, I don't think I assigned it this semester, but there is a problem just like this in the book where they solve it and they end up with, you can't have 2 different concentrations in the same beaker of the same substance. They have to be the same concentration. And so that was like the bonus question at the end. The bonus question at the end, some people try to do this separately at the end of the exam. Try to do those separately, and they'll end up with 2 different lead concentrations. You can't have 2 different lead concentrations in the same solution. Okay, any questions?
There's no change in volume. It's not the same as volume displacement, right? Right.
Volume displacement is usually when you put a solid that doesn't dissolve, an insoluble solid, and then the volume increases. But even when you're mixing solutions, you have to watch out because sometimes volumes are not additive. So it depends on what you're mixing in. with what. Sometimes the volume actually shrinks, sometimes the volume expands. So if you take 10 and 10, you could expect 20, but sometimes you get more than 20, sometimes you get less than 20, depending on how they mix. And that's how they fit between the molecules. So if you have water, it depends on how things fit between the water molecules, how they compact. And so oftentimes it's like if you have a jar of marbles, the classic picture is if you have a jar of marbles and they're all the same size. But what if you put some small marbles in there? Well, if you put some small marbles, let's say I take 10 milliliters of large marbles and 10 milliliters of small marbles and mix them together. Am I going to get 20 milliliters of small and large? No, you usually get less than 20 milliliters because the small ones fit in the spaces better. So volumes are not always additive, but we're not trying to do perfect calculations. Usually we're just trying to get ballpark. If we wanted a much better calculation of this or any of these other ones, probably the best thing is just to use a software package that's already designed for it. Otherwise, the math for simultaneous gets horrendously, I think, difficult. So the software package, I'm going to check it today, but I hope they just fit in Microsoft. Yeah, it's pretty easy to do that. So I need to check with them to see. So I'm going to finish up the chapter 13 homework today or tonight. And I think we only have 2 more problems left on that. So since we're finishing up the chapter 13 homework, I want to have the test for chapter 13 soon, like Thursday. This Thursday. Can you do it? All right. How about the next week, beginning of next week? Tuesday? Oh, is it? Oh, that's right, Memorial Day. Oh, yeah, maybe we'll do it Thursday then. Thursday, okay. No, next week, Thursday. All right, let's, but I want to move on to the next. You'll see, when you go through the homework, there aren't that many different types of calculations. The earlier conceptual stuff, work, what was it? Delta H and delta U, that was from Chem 1A. Probably not going to test you on that Chem 1A stuff, but that's something you should know, and continue on in thermo, because a lot of people, because those are only the beginning. When you go into thermodynamics, there are lots of, you have delta A, you have a whole bunch, and they're all very specific for a specific set of conditions that can only be used when the conditions meet the criteria. Uh-huh.
I have a question on, like, tomorrow, you know, we're doing an actual lab.
Tomorrow is the computer lab, isn't it? Is it the, it's the Visual Mintech, I thought. So maybe I could be wrong. Let me double check that.
This one called.
Visual Mintech, yeah.
And also, what are we doing for the quantitative analysis?
The qualitative analysis lab the report's very simple. The report is you're going to make a list of the cations and the anions that you found, that you tested positive for. But then there's going to be one other part to that. And the one other part is you're going to map out all the chemical reactions in the flow chart. That mapping out, I'm going to do, I didn't write all the equations on the board. So what you're going to do is you can just turn in the list of ions that you tested positive for plus the analysis scheme in terms of chemical equation. And the analysis scheme, I was going to do it on the board, but I figured it's probably easier just to do it on Zoom. It might be easier to read rather than the board. Yeah, I'll just record it. And so he'll just do that. That shouldn't take you know, to run it. That will be the report. I'm going to do that probably outside.
If you do have to use, I think they probably don't do like names and call something specific, like qualitative analysis.
Yeah, definitely. Thermodynamics and kinetics are often combined, but they're related, but then they're two separate. No, in thermodynamics, we're just asking what is the driving force, delta G. You know, but when we do that, we don't care how long or fast, it takes. We just want to know that there's a driving force present. Usually, if something has a long driving force, it could result in a violent, fast reaction. There's a large driving force. It's just a straight shot downhill. But if it's not such a big driving force, then the reaction could be so slow that essentially it just doesn't happen. That is one reaction like that is the conversion of graphite. What do you think is more stable, graphite or diamond? Diamond's more stable than graphite? It turns out under these conditions, graphite's more stable. At extreme pressures and temperatures, then we expect diamond to be more stable. And that's how diamonds form. Diamonds form in these geologic processes. Although some people are trying to make synthetic diamonds. It depends on the synthetic diamond you make. If you don't care about high purity and you don't care about big crystals, then it's pretty easy to make synthetic diamonds using chemical vapor deposition, where you just take carbon atoms and deposit them on the surface. They're called diamond-like films. The diamond-like films have a lot of diamond in them. They also have other things like amorphous carbon and graphite as well. But if you want to make diamonds, you're going to need some high pressures and temperatures. In fact, when I was at UCSB, some friends of mine were trying to make diamonds. And so they're trying to make diamonds using explosions. And so they tried to make charges, that explosive charges that generate a lot of pressure and temperature in the center. They make these spherical things. This is all illegal.
I was like, was this done in the lab or was this done outside?
This was done outside of the lab
I know someone who got in trouble.
at the beach, basically.
Yeah, checks out. Okay.
Yeah. And but the FBI came.
Yeah.
Okay. And one of the guys almost blew off his thumb completely. You knew about that?
No, but I just
Okay.
assumed it.
Yeah, he was walking around. He's actually a student in my class because he was an undergraduate doing research there. He was walking around with lead azide, which is a detonated explosive in a beaker, and it blew up in his hand and severed his thumb. It was hanging by just the skin. Then the FBI came and then quickly put an end to all that stuff. But it was all like innocent. They weren't trying to do anything except make diamonds, synthetic diamonds. I think it was like it's kind of interesting science, but maybe it's their get rich scheme. I've had other friends who are prospectors for diamonds, looking for natural diamonds and that kind of stuff. Apparently one of them found some, but I'm not sure. A large deposit. I lost track. Well, anyway, so how fast reactions occur, we're going to look at next, because if you have diamonds, do you know graphite's more stable thermodynamically And so there's a driving force. Delta G is negative in converting diamonds into graphite. It's not huge, it's like -5 or something kilojoules. It's not huge driving force, but there's a driving force. So what it makes you think is that diamonds are thermodynamically unstable and diamonds should decompose into graphite being more stable. But it's not going to happen. It's not going to happen. It's just not going to happen, basically, because the bonds are so strong in diamond, you know. And so even though there's a driving force, we have a special name for that kind of scenario. The special name for that scenario is metastable. Metastable means this. Means thermodynamically unstable, kinetically stable. That it happens so slow that we don't really have to worry. The reason for that is something called the activation barrier, or the activation energy. So if we have something that's thermodynamically unstable, it's not a straight shot downhill. Normally when we think about this, we think, okay, delta G is negative. So if I have G initial and G final, which would be the Gibbs free energy, and I have a delta G that's negative, in this case, delta G is negative here, and I'm plotting G on the y-axis. We don't do absolute free energies, just like we don't do absolute internal energies and absolute enthalpies. But we do, we can't measure these accurately, but we can measure the change in them very accurately. And so here, what we do, this is thermodynamics here. In thermodynamics, we have the energy level diagram. In kinetics, we see the path it takes. We try to figure out, because in thermodynamics, everything's a state function. So in terms of a state function just depends on the initial and the final state. In kinetics, we're interested in the path things take. And so to illustrate the path that things take, we look at the initial and the final, we spread them out like this. See. Let me put this over on this side. For something like diamond, the path involves climbing this huge peak. And this huge peak is given by the activation energy. The activation energy is how much energy it costs. So for example, if we're starting with diamond over here, and we want to get to graphite, it's not a downhill stretch. The first thing we have to do is break all of the bonds in diamond. How easy is it? Well, it's not easy, because those are sp3, sigma bonds and a covalent network lattice, which covalent network lattices have extreme melting points. Have you ever tried to melt diamond? To break the bonds? Or quartz? Have you ever tried to melt quartz? It's not easy to do. You need extreme temperatures for that. And so because of that, you aren't exposing your diamonds to such extreme temperatures in order to break those bonds, so it's going to be kinetically stable. This activation energy is too high. Now, if something has a much easier path, then it should happen quickly. And so it depends on how big this hill is. A big hill here is going to happen slow. A smaller hill is going to happen much faster. But there's usually always a hill. Even for endothermic reactions, we have a hill to climb as well. And so this would be an easier path than that. And so it depends on how big this path is. So a lot of reactions, you don't want to wait very long. And so a lot of chemists spend their time thinking of alternate pathways. These pathways are called mechanisms. So they're trying to think of alternate mechanisms because there are lots of examples of alternate mechanisms. Like, for example, in biology. In biology, they have things called enzymes, and enzymes are catalysts. And catalysts, what they do is they provide an alternate path to lower the activation energy to make the reaction happen faster. And so if you're looking at hydrolyzing like sucrose in your stomach, it's very slow. It takes if you ate sugar and you didn't have these enzymes, it'd take like an hour or many hours in order to get the sugar rush. But what you do, that's because the normal pathway for hydrolyzing or breaking apart the sugar has a fairly high activation energy and it just happens slowly. But with these enzymes, sucrase, it happens extremely fast. So you get an instant sugar rush, which is a good thing if you need that. Maybe some people don't need it. Maybe some people need to disable that enzyme temporarily. Get the blood sugar more. But anyway, getting back to this. So we're looking at the path. And so this is very interesting. How do reactions occur? And so that's what we're going to start thinking about. So let's take a look at this reaction here. If I think about the reaction of methane and oxygen, is there a driving force for that? What do you think? Is delta G positive or negative for the reaction of methane with air, oxygen? If it's positive, then it's not going to happen. So if I released a whole bunch of methane into this room, would you feel uncomfortable? Well, one thing, it's going to smell a little bit because they put an odorant in there. Otherwise, methane's non-toxic. Right? So I don't mind inhaling methane. It's not going to do anything, really. It's pretty unreactive. But would you feel comfortable being in a room filled with methane and air? No, not really. But nothing's happening. So if nothing's happening, then I think we're safe, aren't we? Yeah, one spark, and it's going to ruin everything. And that's because if I think about methane and oxygen, the gases, this is what we call a metastable mixture. It's metastable because one little spark will get enough to go over the hill. Once you get enough to go over that hill, then the downhill part releases enough energy that we no longer need a spark. So this is just a spark to initiate the reaction. But once the reaction starts, it's sustained because of the energy that's released in this. So we climb up the hill, and then as we go down the hill, we're going to have this much energy. And then CO2 and water are thermodynamically stable. It turns out it's not a simple hill like this. Like, for example, have you ever wondered why is the flame blue? Why is the flame blue? Oh, it's got to be the water. Water is blue, right? And therefore the flame is blue because it's creating water, and water, like the ocean's blue. Is that? No, it's not correct. So why is it blue? And what is a flame? What's inside the flame? Well, the flame we say is the fourth state of matter. And the fourth state of matter is what? Plasma. So we have solid, we add energy, liquid. Liquid, we add energy, gas. Gas, we add energy, and what happens is you get violent collisions. These violent collisions result in ions being formed. And so plasmas, they have two types of plasma. The first type of plasma is like a partially ionized gas, and the second type is the heavily ionized gas, like the sun's plasma. The sun's plasma is heavily ionized gas. That would be called a thermal plasma. And then these partially ionized plasmas, like although those are LEDs, but in the old fluorescent lamps, those were partially ionized plasmas, which are called non-equilibrium plasmas. But anyway, we'll have a thermal plasma generated here, and in that thermal plasma, there are a whole bunch of stuff. So people were very interested in the path. It's not a simple path like this. It's a very complex path. And this complex path has lots of peaks and valleys. In fact, when you look at it, and then lots of different ways that things can go. And it wasn't until about the 1950s when this was fully sorted out, when they thought, okay, we have it now. We can kind of understand what's happening in flame. And you think this reaction's been around for how long? And this reaction's been around for ages, but it wasn't really well understood what happened in the flame. And it turned out there are like thousands of potential reactions that are occurring in that flame and generating not thousands of species, but lots of different species because of branches that end up at the same place. And so, well, how do they figure this stuff out? Well, they figured a lot of this stuff out using kinetics. So kinetics, there are two major groups that are into kinetics. You have these people who are very interested in what's happening in the reaction at the molecular atomic level, and generally those are like the physicist types and the biochemists or the biologists. And the biologists are very good at kinetics because they want to know the mechanism of what's happening. And so this chapter is going to be divided into two parts. Basically, the first part of this chapter deals with just the math. We just see what happens when we get together. So it's just empirical, mathematical, not really theoretical analysis. Theoretical comes later, which is in the second half here. The first half is all empirical. The second half is looking at it in the more theoretical context, because it's more about how to do it. What's happening is primarily the mechanism, reaction mechanisms. So normally when something has a big driving force, we expect it to be a violent reaction, so delta G, and that's typically the case. Something has a big driving force. It's going to either be highly metastable, like this has a big driving force. So you should be very uncomfortable if somebody were, if you have a gas leak, you should be very uncomfortable. In fact, was it a couple of years ago? I think I mentioned this before. There are lots of cases with big buildings blown up. But you have unstable stuff like this. This one's not too bad. This is the volcano reaction. This is ammonium dichromate. Why is ammonium dichromate unstable? Well, what kind of reaction is that? Redox. Yeah. What's the oxidizer? Oxidizer is a very common oxidizer. It's a good oxidizer. Nitrogen is not the oxidizer. Dichromate. Dichromate is an excellent oxidizer. Why is a dichromate an excellent oxidizer? Yeah. Well, the chromium and dichromate. Dichromate and chromium both have chromium 6. And chromium 6 will max out, it's fairly high. This is electron 4. So dichromate's the oxidizer. What's the reducer in this? ammonium. Ammonium is, nitrogen is minus in ammonium. It's NH4 plus. Minus 3. Minus 3 is pretty electron rich. And so ammonium dichromate is metastable. Anything like this where you have, I mean, this is in the same compound. What's preventing these from reacting? What's preventing these from reacting is they're, as long as the temperature is low, they're just vibrating in their lattice positions. What happens if you increase the temperature? If you increase the temperature, you better watch out because those vibrations can get big enough that they can start to react. And dichromate wants the electrons that ammonium has. And what's preventing it is they're just staying in their place, they're behaving. But if you heat it up, this is what's going to happen. You're going to get, and if that happens very quickly, then you can have an explosion. Explosions are just very rapid reactions that generate a lot of energy, and that energy has to be dissipated very quickly, and so it causes damage, kinetic energy. And so all that chemical potential energy is converted into kinetic energy, the change in chemical potential. So nitrogen is fairly stable. This is water gas. This is a potentially explosive reaction because what happens is the volume expands quite a lot. As we go from a solid to 5 moles of gas, and so the volume expansion, 5 moles of gas is approximately how many liters? At room temperature and 1 atmosphere. Did you have to memorize 22.4? Did you have to memorize that? No? Okay, you're lucky. You're lucky. I had to memorize that. I wish I could get rid of that to make more room. I ran out of memory a long time ago, but I can't get rid of that. I wish it's like one of those things that's totally useless that I can't get rid of. Whereas the important stuff I can't remember, which is frustrating. But anyway, the one I would have found more beneficial to memorize is a mole of gas is approximately what volume at room temperature in 1 atmosphere. Well, at room temperature 1 atmosphere, 24 and a half. We call it 25 liters. At 1 bar, it's a little bit bigger, because a bar is a little less than an atmosphere. And so the volume is going to expand a little bit more. So like 24.7. Those are useful numbers to memorize because then you can do work calculations much quicker. I mean, there's a lot of work in generating 5 moles of gas. And so that's going to take up some of the energy, that's generated in this. There's going to be a certain amount of chemical potential energy between these two, which we call delta G. But, when we want to think about this in terms of how much usable energy we have, well, delta G, another way of thinking about delta G is delta G is the amount of energy that can be used to do work. So some of the work we could do is expanding the gas. Then we could do other work like light is work, heat, and we can convert that energy into heat as well. And so this one, if you didn't know this from experience, this I would think, and I'd watch out, this could be a very violent, very explosive reaction, but it turns out to be a very gentle reaction here, and it makes these volcanoes that they do as demonstrations, but in this case, you can never be sure. And so this is just based on empirical. Somebody's done this before because if you have a scenario like this, you got to watch out. That could easily cause you trouble. There are other things that are slow, like this, like milk. usually when they do food tests, they don't, like, if they do shelf life tests, they normally don't keep it on the shelf for that long, and then, okay, that's how long the shelf life is good for. Normally what they do is they do something accelerated, like they'll do it and they'll put it in the oven or they'll subject it to this. And then from that, they'll do a calculation under normal conditions, how long would that last? Like spoiling milk or whatever else, to get the shelf life of that. So kinetics can be pretty useful in determining that kind of stuff as well. I also said, like pressure cookers or high elevation cooking, that's all kinetics. And where did I get the 10 degrees C? This is something I also memorized when I was taking Chem 4. That for every 10 degrees C temperature increase, the reaction rate doubles. But that's only good for things like food. It really depends on the reaction because it depends on the activation energy. Food has a pretty low activation energy when you cook food. And you don't completely destroy it, like cooking eggs or whatever else. And so in that case, it works. But things with a much larger activation energy or much smaller activation energy, it's not going to be so good. That rule of thumb. There are exceptions to that rule of thumb. There's some calculations in this, in the homework, that will go through that. All right, so what we're going to do is we're going to do this empirically. And so what I'm going to do here is we're going to take a look at the data from the lab. I have the data here, and I want to do the kinetics data in addition. So I'm going to check and see. Now, if there's a backlog with, I'm not sure how short-staffed they are over at the, what's that office called? Well, the computer office, whatever the name is. If they aren't going to be able to get to it this semester, maybe they'll let me, but I doubt they're going to give me the password to be able to update it. But I'll make one effort to get it done today, or at least let me do it so I can get it done. But if not, we're going to just work up our kinetics data. When we do our kinetics data, the first thing we're going to do is we're going to do a Beer's law plot. And so this is not kinetics here. But we need to do Beer's law plot. And that's plotting absorbance versus the concentration. This is the concentration of crystal violet chloride, or Cb+. This is a ionic compound. So crystal violet chloride, when it dissolves in water, the ions split apart. And we have this crystal violet ion. Crystal violet ion is an organic ion with a positive charge. And there's just the structure of it in the lab. Okay, and then we're going to generate a plot. If we have zero concentration, we expect zero absorbance if it were properly calibrated. So although we didn't measure it, normally we have it go through the zero, the origin here. And then we'll take a look at our data here. And we got 3 data points. It depends where they are. Okay, then what we're going to do is we're going to fit this to the best straight line, because we should be, as long as our absorbance is below what? We should be in the linear part of Beer's law. Yeah, as long as our absorbance is below 1. Now, if our absorbance goes above 1, we can still use that data, except it's just curved. And then there's going to be a much larger error associated with that. And so this is why we try to keep it below 1 here. And what we're going to do in Excel is we're going to do something called a trend line and linear least squares fit in Excel. We may have done this before. So if we do linear least squares fit, it tries to minimize the deviations to get it to minimum here in the line. But you don't have to do anything because the Excel should do that automatically for you. And it's going to generate an equation for the line, which is going to fit this y equals mx plus b. But b in this case is going to be 0, or it should be 0. Sometimes we don't because we're off, reading off, and there's some systematic error for this. And so we're going to get some line here. Then we're going to just make sure we have enough digits. We can, Excel can either expand the number of digits or reduce the number, depending on who used it last. So if you're only getting one sig fig, it's not good. We need a lot of sig figs for this because we're trying to avoid grammar error. We get some numbers in this. In fact, we're primarily interested in one number, and that's the slope. We want to get the slope to as many digits as possible. There's something called the R squared value, and this is an indication of how well the data points match the line. If it was a perfect match, do you know what the R squared value is? Yeah, 1. Yeah, that means the data and the line are perfectly matched. And so here, what we're looking for is as many 9s as possible. And so if there were only 2 data points, then obviously it's going to be a perfect match, but we're going to have more than 2 data points. And so the more 9s, the better. And so we're looking for at least 2 9s, maybe. For a decent, 3 9s would be better. The more 9s, the better. What if we have like a 0.8? A 0.8 is not good in science. It depends on what type of science. In the social sciences, I was listening to a social science talk, and they said a good correlation there is like 0.6, 0.7. Because of human behavior and that kind of stuff, it's hard to get decent correlations. But in the sciences, we expected not, high 9s, sure. And so the more the better. So we'll keep an eye on this and see our data. Sometimes this tells us maybe we inputted the data wrong. So if one of these drops way down here, it's going to throw off our square. All right, once we have that, then this equation is y is equal to the absorbance is equal to the slope m times the concentration x. Okay, that's good for us because what we're going to do is we're going to plug in all our absorbances. And so we're going to have a time and absorbance data. I don't know, I'm pretty sure it's time first, then absorbance. And so we're going to input these manually by hand. Well, the time, since regular intervals, Excel can fill that in. So if you put in the first 2, it'll recognize the time trend, and then you don't have to input it by hand. What you'll do is you'll take the first 2 and then copy and paste it down, and it should, at least it used to in the previous version of Excel. But I had trouble with the recent version of Excel where it just kept copying and pasting the same. But usually it just fills in the trend. And then you're going to input the absorbances manually by hand. Actually, you don't have to do that, do you? Sorry, you don't have to do that because the data is already formatted in this. You just import it into Excel, so forget that. We used to have to do this by hand, but we don't have to do this by hand anymore. That's why we used to only collect data at like 45-second intervals. So you didn't have a mountain of data that you would have to input here. But we could collect the data in millisecond intervals. It made a big difference. As far as work goes, because okay, then what we're going to do is we're just going to calculate the concentration. The concentrations just over here, it's just C equals the absorbance over the slope. So we'll just plug that in here. Concentrations equal to the absorbance over the slope, and then just calculate those. And then we're going to make a plot of concentration versus time. And so we're going to plot these two. And then let's take a look at what it looks like. Okay, when we do that, this is what it's going to look like. This is this is based on the absorbance of crystal violet, and this will be the concentration of crystal violet. And so this will be the crystal violet concentration. The crystal violet concentration, let's say at time 0 or whatever, your initial time here, whenever you got it into the spectrometer, is what we'll call time 0, is up here. And then at the next time, it's reacting. So the concentration of the crystal violet is going down as its color is decreasing here. So what we can do is we can look at something called the rate of reaction. The rate of reaction is given by the change in the concentration. We'll just call it A, generic. In this case, it's going to be the change in the crystal violet concentration over the time interval. That would be the rate of reaction. And so basically, it's just figuring out the slope, delta y over delta x. Just figuring out the slope of this line here. The slope is the concentrate, the slope is the rate. Well, what do you think is going to happen? Well, at the next data point, it could be the same rate, or what we see a lot in kinetics is the rate starts to slow down. And in fact, that's what happens in our reaction. The rate starts to slow down. We see this trend in our data that looks like this. You probably already saw this. Did you already see this when it plotted out the data from LabQuest? Yeah. You saw that it's a curve. Now, how should we describe this curve? Should we describe this curve with a straight line? Said no. Probably the best way to describe the curve is just to draw a curve. And so we should draw a curved line here to describe this. When we draw a curve like that, then we see something. If it's curved like this, the rate is changing continuously. And so that means when we talk about the rate of reaction, we have to add a couple of things to that. One thing we're going to say is that this is not just the rate of the reaction. We're going to call this the average rate of reaction over the time interval. So average rate of reaction over time, this to this. So this would be the average rate of reaction from time 0 to the first time we took here would be it. But we can see that even within that time interval here, it's changing, you know. And so what would be a more maybe a more descriptive would be to look at something called when this reaction first starts out, the slope is quite big, but when we hit this time interval, the slope has already gone down. Do you see that? So if I look at this time interval, the initial slope is kind of big. And this initial slope, we're going to call this the initial rate. The initial rate is what we say is the instantaneous rate at time zero. So initial rate equals the instantaneous rate at time zero. So the problem is drawing a tangent. This is what we call in math a tangent. You guys are familiar with tangent lines? Right? Okay. So drawing a tangent line at time zero is not so easy. And so what we often do is we say that this is going to be approximately equal to the average rate if less than 5% reactions occur. And so if this is 100%, and then we go to about 95%. And so between 100 and 95, we can take the average rate there, and that would be close enough to the instantaneous rate. And so it's approximately equal to the average rate with less than 5% reaction. And so we've only consumed 5% of our initial. Then we could say the average rate is close enough. So the average rate would be pretty close. You know? So if I did 5% of the initial, it depends if I have a data point here. You know, but let's say this sort of 100%, so about 5% would be about here, and then we take the average rate between 100 and 95% here of our initial, and then that's going to be close enough. Does that make sense? This is also, the average rate here will be the average of the initial instantaneous versus the final instantaneous rate there. Or we could just take the average over the entire range here. The average over the entire range would be like this. But we can do that if we're just kind of approximating. So here, the slope is changing. Here. So we have something called the rate law in the well, let's see what I want to talk about. I'm trying to go in order of the book. Oftentimes, we just are interested in the initial rate. And so if we have a reaction AA plus BB plus ... goes to product, then the rate law is equal to something called the rate constant times the concentration of A raised to the m power, the concentration of B raised to the n power, ... The rate constant comes from a couple of things. It comes from like the mechanism and how successful. And the mechanism deals with equations and other kinds of stuff. So something with a large rate constant happens fast. Everything's in favor of fast reactions. Something with a small rate constant happens slow. It's just mechanistically, it's just slow. So it varies depending on the reaction and the mechanism of that particular reaction. And if there's a catalyst present, then it makes K big. If there's no catalyst present, it makes K small. M, N, etc. are called the order. So M would be the order with respect to A. And so what's typical for the order would be like zero order. If M were zero, then we would have A to the zero, which is just one. Has implications on what happens. And so the rate law is that the rate can be calculated. So the rate is equal to K, A to the M. If M is equal to 1, then what happens here is this. If it's first order in A, I can see what happens with the concentration. So if I double the concentration, the rate would double. If I cut the concentration in half, the rate would be cut in half because it's just 1/2 to the M order, it's the first. Whereas if M were second order, if I double the concentration, the rate would quadruple. Or if I cut it in half, it would go down 1/4 the speed. And so we can see like this in terms of the plot. I can see this based on what the curve looks like. Although this is maybe hard to see initially because we need some more data, some more calculations. This is a first order decay. How I can tell it's a first order decay is I can look at the instantaneous rate here. Oops, not such a great. And then look at the instantaneous rate here. And I'm going to call this A, the concentration of A here. And if I look at the slope is half. And then if I go here to here, so I start at this and then cut the concentration in half, the slope gets cut in half here. And then I start here, cut the concentration in half, the slope gets cut in half here. There's an easier way of doing it. And maybe it's hard to see the slope. The easier way of doing that is this. When I have a first order decay like this, a first order decay, this is the rate is equal to Ka to the first. Is I have something called the half-life. That is the time it takes for it to consume half the original. So if I start off with the original here, eat up half of it, it takes this long. Okay, then I start here and eat up half of it. How long does it take? It takes the same amount of time. Then I start here and eat up half of it, although my drawing might not be so precise. So, although it's hard to just eyeball the slope and see that the slope is being cut in half, it's probably a lot easier to see. This is the pattern you'd expect when the slope gets cut in half each time, or the rate gets cut in half each time. So this is what we call first order. This is very different than if we had zero order. If we had zero order, let's say the rate were equal to Ka to the 0. That would be zero order. And the way it would look is like this. Okay, so the first half-life takes this long. The next half-life, the different ways you can visualize this. One way is, as I change the concentration, let's say I cut A in half, what happens to the rate? Well, nothing happens to the rate because A is to the 0th power. Anything to the 0th power is just 1. And so what we're going to see for the rate for this one is it's just going to be a straight line. It's probably easier to see in terms of slope. The slope does not change. Rather than half-life. If we did this in half-life, then we'd see an interesting pattern in the half-life. The first half-life is twice as long as the second half-life. So this is going to be 1/2 of the original half-life here. And each subsequent half-life is going to be half as long as the previous half-life. And so it just gets smaller and smaller. But anyway, this one's easier for the slope because the slope just stays the same. This one's probably easier to analyze based on half-life. So this would be the characteristic pattern of that. And then the other common one is second order. And so let's do that here. This is where K and the dependence on the rate on the concentration squared. So it looks like first order, but it's flatter. And so the first half-life, let's take a look. And look at the first half-life, it takes, let's say, this long. So that's the first half-life. But the second half-life is going to take twice as long as the previous half-life. So it's a lot flatter. And then the next half-life is going to take double the previous half-life. So this would be 2 times the previous half-life, which would be that. And so each successive half-life doubles in time. And then you know it's got this second order. And so the order is important because it tells us how it's going to behave with concentration. So when we look at our crystal violet, we can tell immediately, does this look like first order? Does it look like second order? Or maybe something else? We can tell by kind of estimating, okay, if I go here, half of it took this long. When I go for the next half, it took this long. So it kind of looks like first order. And so we can see this based on this curve. But there's some mathematics that we can do to analyze the curve, which we'll talk about tomorrow. Are we out of time now? Or do we have another? Do we go to 11:10? 5 minutes, or then we can talk more. Okay. So to analyze this curve, there's one problem, and that's what's happening with the hydroxide. When we see the rate decreasing, the rate is also going to depend on what's going on with the hydroxide. And so for our curve here, the rate law, well, let's look at the reaction first. The reaction is crystal violet plus hydroxide yields crystal violet hydroxide. And the rate for this, the rate law is going to equal K times the crystal violet concentration to the N power times the hydroxide concentration to the N power. Now, why can't we use a coefficient here? Because the coefficient is 1 and the coefficient here is 1. We can't use the coefficient here because we don't know what the mechanism is. You know, what's happening. So, for example, when we look at the burning of methane, it just simply says that one methane requires 2 oxygens to form CO2 and water. 1 CO2 and 2 water. But what's actually happening mechanistically is much more complicated. And so even though this looks like a very simple reaction, you know, if I double the crystal violet, then I should get twice as many collisions and it should go twice as fast, you know, with a higher concentration. Or if I double the amount of hydroxide, I'm going to have more hydroxide. It should go twice as fast, right? But mechanistically, we need to know what's going on, you know, because the mechanism can be quite complicated, a lot more complicated. So we don't know what M and N are. M and N are determined theoretically. If you know the mechanism, we can determine what M and N are, but more commonly, they're determined empirically. We just see what happens. And so what we do is we'll change the crystal violet concentration, see what happens to the rate, and hold the hydroxide concentrations constant. Now, the problem is we have 2 unknowns. And if I'm only monitoring the crystal violet here, you know, at the same time crystal violet's changing, what's happening with hydroxide? It's also changing. In fact, for every crystal violet that reacts, I have to have 1 hydroxide react as well. So we know that this is going to happen. And that is the rate of crystal violet consumption, the rate of crystal violet reaction is equal to delta change in crystal violet over delta T. Now, there's one thing that happens. We like to talk about rates not as negative or positive. We like to just take the absolute value of the rate. And that is, and then use the word consumption. This should be negative because final is smaller than initial. This is going to equal the rate, because it's a 1-to-1 mole ratio, it's going to equal the rate of hydroxide consumption as well. And so the rate of the crystal violet is equal to the rate of hydroxide. So both of these are being consumed. And so what's going to happen is a compounded effect, you know, because let's say, is it time? All right, let's say it's a compounded effect. That is, when the crystal violet concentration gets cut in half, the rate gets cut in half. But when the hydroxide concentration gets cut in half, the rate gets cut in half as well. And so that's 1/2 times 1/2. And so if both get cut in half, then the rate should get slowed by 1/4. 1/2 times 1/2 gives us 1/4, and we should expect 1/4 the rate because it's a compounded effect. And so we need to determine that. We need to determine, you know, what is the effect of crystal violet on the reaction? What is the effect of hydroxide? But we have a sneaky trick to get around this. Do you know what the sneaky trick to get around this is? The sneaky trick to get around this is we're going to hold the hydroxide concentration so huge it barely changes during the course of reaction. So what we're going to do is we're just going to flood it with so much hydroxide that initially the crystal violet concentration will decrease significantly, but the hydroxide concentration will barely change. Does that make sense? Okay. And so what we're going to do is we're going to make the reaction what we call pseudo M ordered. And so what we're going to do is we're going to have initial concentration of hydroxide so large that when we do the minus X here, it barely changes, whereas the crystal violet changes significantly. So we'll have like 90% reaction of the crystal violet, but only like 0.1% reaction of the hydroxide. And so hydroxide initial is very large. Therefore, hydroxide final is about equal to the hydroxide initial. And therefore, the hydroxide concentration is relatively constant. And so if the hydroxide concentration doesn't change during the course of the reaction, then the only thing changing is the crystal violet. And if the only thing changing is the crystal violet, then we can determine what the order is. Because we want to know the order. We want to know, well, we know it's not zero order because it didn't give us a straight line, but we want to know, is it first order or second order here? Now, calculus has a way of doing this easily. That is, there's something called the integrated rate law, but we're out of time for that. And so we're going to do some more calculations here. The more calculations we're going to do on the spreadsheet, or let me just do this. We're going to take the natural log of the crystal violet concentration, and then we're going to take the inverse of the crystal violet concentration. Do those, and then we'll make some more plots, and then we can see, is it zero order, first order, second order, but you probably can tell just by looking at the graph what order it is. Okay. All right, so tomorrow we're going to go straight to the computer lab.